Okay, so this is a quick review of the derived rules and equivalences. So these are the power tools for doing propositional logic deduction. The basic non-derived rules can be thought of as the hand tools. And it's important to understand that there is nothing that we can do with these derived rules and equivalences that we can't do with the hand tools. And the reason for that is very simply that the only reason we can use the derived rules and equivalences, the only reason we can use these power tools is because we built them with the hand tools. That's to say, we used the non-derived rules to prove all of the derived rules and equivalences. Now, of course, we didn't do them all ourselves, but we did do quite a few in previous homeworks. So let's just go quickly through the derived rules first. The first one is called hypothetical syllogism, and it's very familiar. It just tells you that if you have if A then B, and if you have if B then C, you can assert that if A then C by 1-2 hypothetical syllogism. This is a rule that we proved in a previous homework, and we had to prove it using conditional introduction and conditional elimination. Next rule is modus tollens. Modus tollens says that if you know if A then B, and if you know that not B, then you know that not A. So a very intuitive rule, almost as intuitive as its sister ponens, which we actually call conditional elimination. It's the modus tollens is sort of modus ponens run in reverse, right? So conditional elimination says if A then B, A therefore B. Modus tollens says if A then B, not B, therefore not A. In philosophy, we sometimes say one person's modus ponens is another person's modus tollens. And what we mean by that is that you're always free to deny or negate the conclusion that is reached by modus ponens, as long as you're willing to deny one or more of the premises. Next one is disjunctive syllogism, and that tells us that if you know A or B and you know not A, then you can conclude that B, or if you know A or B and you know not B, then you can conclude A. So again, 2 lines, 1-2 disjunctive syllogism. This rule, which we also derive, is extremely useful because it often will get you out of having to do a disjunction elimination. Not always, but sometimes, as we'll see. The contradiction rule is interesting. The contradiction rule says if you have a formula A and its denial not A, then you can simply assert that B, and of course by B we mean any formula that you like. This is a fact that's kind of good to have in your back pocket. A contradiction implies anything, and it's actually very easy to explain this if you're trying to explain it to somebody else. Pretty much here's what you'd say. Say, look, suppose you have P, and let that be any formula whatsoever, and suppose you have not P, let that be any formula whatsoever. Now, why does this imply just anything? Well, there's a rule called or introduction that says you can derive from P, P or anything you like. So let's say P or R by 1 and disjunction introduction. The reason we can do that is because if we know that P is true, then P or anything else is true. That goes back to the meaning of the truth table for disjunction. But now that we have P or R, we can infer that R, right, by the rule we just learned, 2, 3, disjunctive syllogism. So contradiction actually comes in very handy, as we'll see later. But it's very important to understand that contradiction is different. It's not the same rule as negation introduction. Both of these capitalize on contradictions, but they do so in their own way. Contradiction doesn't require you to hypothesize the negation of what you're trying to prove. It just points out that you are currently given a contradictory state of sentences, so you can simply write anything you like. The repeat rule, very simple. If you have A, you can say A. Okay? This is something that we had to finesse before we had this rule, but now we have it. And so if we ever need to repeat a line, we just write 1 RE. And finally, for our derived rules, we have constructive dilemma. And this is just sort of a specific version of disjunction elimination. And we've actually proved this rule in the past. It tells us that if we have A or B, and we know that A yields C and that B yields D, then we can state C or D. So just like disjunction elimination, there's 3 lines cited, but you would cite CD for constructive dilemma. This is not a terribly important rule to memorize, since it's very easily derived just using or elimination. Okay, that's it for the derived rule. Those are by no means all of the derived rules. There's an infinite number of derived rules, but these are just the ones that we find it handy to memorize for the purpose of making much shorter work of proofs. The next thing we have is equivalences, and equivalences are equivalent formulas, and they're represented not by a single turnstile, but by a double turnstile, which means that one can always be derived from the other. So the first and probably most famous equivalence is called the De Morgan's equivalence, or sometimes De Morgan's rule. And they are very much reminiscent of the tree rules, but they go both ways. So what does that mean? It means that if you have, it's not the case that A and B, then you can at any point substitute not A or not B. Alternatively, if you have not A or not B, you can at any point substitute it's not the case that A and B. Similarly, if you have it's not the case that A or B, you can at any point substitute not A and not B, and vice versa. Now, it's very important to understand the power of equivalences. They can be used like derived rules, but because they actually represent logically equivalent formulas, this means that you are not restricted to working on the main operator as you are for all of the other rules. So derived rules, non-derived rules, you have to always be working on the main operator. So just to make it clear, we just learned De Morgan's. So what does that mean? Well, suppose on line 1, you had this formula. If P, then it's not the case that A, and it's not the case that B. Okay? Suppose you have that. Now, the main operator is the conditional, right? But with equivalences, we're not restricted to working with the main operator. So if we wanted to, for some reason, we could write, if P, then it's not the case that A or B by 1 and De Morgan's, right? Because this formula here is equivalent to this formula here. So that really speeds up proofs, and it's very important to understand this is something you can do with equivalences. It is not something you can do with plain old derived rules or underived rules. Okay, next equivalence is called transposition, and it tells you, it tells you that if A then B is logically equivalent to if not B, then not A. Now you can prove this very easily in the forward direction simply using modus tollens. You can also prove it in reverse direction using modus tollens, but you also need to use negation elimination. Okay, material implication is an equivalence between the conditional and the disjunction, an equivalence that we actually described when we were using truth tables and explaining the truth conditions of the conditional in terms of the truth conditions of a disjunction. It tells us that if A, then B is logically equivalent to not A or B, and of course vice versa. Negation conditional, again, familiar from the tree rules. It tells us that it's not the case that if A, then B is logically equivalent to A and not B. This was one of the fun ones to prove. Requires a little bit of creativity, but still relatively straightforward. Commutation is kind of a relief to come by because a lot of you have always been sort of frustrated by the fact that we couldn't do this already. Very similar to math with addition and multiplication. In this case, A or B, logically equivalent to B or A and B, logically equivalent to B and A. So you can substitute rearranged versions of these formulas now. Double negation is simply telling us that A is logically equivalent to not A. Now, until now, all we've had was negation elimination, so effectively we've only been able to go in the reverse direction. Now, you can really just forget about negation elimination entirely and just always use double negation because it gives us both directions. Association is a rule that applies to strings of conjunctions and strings of disjunctions. Okay, so as long as you have a string of conjunctions or a string of disjunctions, it doesn't matter how they're grouped. So A and B and C, logically equivalent to A and B and C, and the same for disjunction. And finally, distribution. Distribution tells us that if you have a conjunction between a formula and a disjunction, then you can distribute in such a way as to create a disjunction of conjunctions. So if you have A and B or C, that's logically equivalent to A and B or A and C. Alternatively, if you have A or B and C, that is logically equivalent to A or B and A or C. And again, of course, because it's an equivalence, you can substitute these within formulas and you can go one way or the other. Okay, so one last point before we go into the homework review, and that is that when you're using equivalences, it's really important to manage your negations correctly. So for example, suppose I have on a line, on say line 1, P and Q. And I just have that as an assumption. And let me actually just give us a little proof to do. Suppose I say I want to, from P and Q, I'm going to write it down here. From P and Q, I want us to derive that it's not the case that not P or not Q. Okay, so how would I do that? Well, I'm going to do it via De Morgan's, but I can't just do this in one step. What I've got to do is say, okay, I've got P and Q. That means I've got not P and Q, not P and Q by 2 and, now I'm just going to say double negation, and that means I've got not P and not Q by, excuse me, this should have been 1. Hope you got that. 1 in double negation, right? And this would be not P and not Q by 2 in double negation. And now the logical form of this formula here is now not A and not B, right? Where our A is not P and our B is not Q. Okay, so now I can apply this equivalence in the reverse direction by De Morgan's to write it's not the case that not P or not Q. And that is just going to be by 3 and De Morgan. I think most of us have a tendency to remember the left to right direction of the equivalence better or more easily than the right to left direction. So if you want to check what you've done to make sure it's correct, just run it the other way, right? So can you get from 4 to 3 applying De Morgan's? And as a matter of fact, you can. Okay, one more. Suppose I wanted to show, suppose I was told to show if, show that P or Q yields if not P, then Q. Now, a perfectly good way to do this would be to use conditional introduction and disjunctive syllogism. Nothing wrong with that at all. But suppose you were thinking you wanted to employ the equivalence of material implication. Now, material implication tells us that if A, then B is logically equivalent to not A or B. Now, you absolutely can use this, but you want to notice that P or Q is not in this form, right? The first disjunct has to be negated. So that's very easy to correct. We just do it in the same way that we did De Morgan's before. So we have P or Q as an assumption, right? And then we just go to not P or Q by 1 and double negation. Okay, so now not P corresponds to A. Not P corresponds to not A. And Q corresponds to B. So since not P is our A, this gives us, by the material implication equivalence, if not P, then Q, right? So just in 2 steps, 2 material implication. So that's the main trick or the main stumbling block to using equivalences effectively, and that's simply managing your negations normally in accord with the double negation rules so that you really are operating on the correct formulas. Okay, that's it.